हम लोग के बीच में है आज वो, जो कि बहुत ही इंटेलिजेंट एंड प्रोविडेंट स्टूडेंट था. Now he has done Bachelor of Science from the Lucknow University and he got gold medal in physics in 2011. Master of Science from this Chemistry department in the year of 2013. Now presently he is doing his doctorate in chemistry. He has got doctorate fellow at Department of Inorganic and Physical Chemistry, Indian Institute of Science in Bangalore. His research topic is tetrahedral Raman spectroscopy, instrumental aspects and practical applications. Now I welcome please start with it.
Thank you very much. Am I audible at the last? Thank you very much for calling me. As a question, so today I am going to discuss. I have divided my talk into two parts. First, I discuss the basic spectroscopy part, and second, I discuss what I have done in my doctoral research. So this is the place from where I come. Yes, sir. Hello, better? Yeah, so this is the place from where I come, and Bangalore is famous for its lights, and Bangalore has lights in all the possible domains. You can see that we have a very high social life here, but there are different kinds of light with which I am associated right now. So let's jump first at what is spectroscopy and what do you mean by it. So spectroscopy basically means when you interrogate matter with the help of any electromagnetic radiation. So be it visible light, be it X-rays, anything, but you interrogate it with the help of light. Okay. So then what you do is whatever spectra, whatever light information you are getting, either it is in scattered form or emission form, you read that light with the help of different methods. Okay. So what you are doing is that a beam of radiation is passing from a source such as laser. So this pointer which I am using right now, it's the feeblest example of a laser right now. Okay. This is a 633 nanometer laser. That's why it's red in color. Okay. So what you are doing is you are passing a source light, and then the radiation which is coming out, you are just taking that and reading that statement. So basically, molecule is telling you what's happening with it with the help of radiation. Okay. So let's understand the Jablonski. It's very famous. We all are familiar with it. If you are in the ground electronic state right now, and you are just transitioning within the electronic state, it's called the vibrational transitions. Okay. So I have shown it from 0 to 4000 wave number because that's typically the range in which the vibrations are happening. Whether it's the bending mode, stretching mode, asymmetric bending, all kind of things. So this is happening within this range. But when you go to another states which I have not marked here, if you see that there is no state here, this is called as an imaginary state. Why it is called imaginary state? Because the lifetime is 0. You cannot populate it. There is no method of populating it. All the things which I have shown by dashed line or solid lines, they have a particular lifetime. And how do you know the lifetime? Because of the Heisenberg's uncertainty principle. Okay. But if you see carefully, I have not shown anything in Stokes and anti-Stokes part because that's an imaginary lifetime. Okay, so you cannot actually populate these states. And this, what we call is the Raman spectroscopy. So Raman spectroscopy gives you almost similar information as IR, but the difference is that IR is an absorption technique, but Raman is an inelastic scattering. What do you mean by inelastic? When you have exchange of energy between two colliding particles. Alright? Then when you jump from one electronic state to another electronic state, so these are whatever I am saying here, electronic states, quantum mechanically these are eigenstates, true eigenstates of the system. Alright? So when you take jump from one electronic state to another electronic states, these are known as electronic absorptions. Okay? So what you are doing is now you are not perturbing the vibrations of the system, but rather you are involved with the electronic system directly. You are probing the electronic cloud directly. And when you come back, because we all know that whenever you excite something, it cannot remain to that state forever, so it has to decay after a certain lifetime. And decaying has different mechanisms. It can be radiative, it can be non-radiative, we all know that. So one of the phenomena by which it can decay is known as fluorescence. Fluorescence is a radiative part, but people who are doing Raman spectroscopy, fluorescence is a trouble. Why? Because fluorescence has a very high background and Raman is a weak process. So if a sample is giving fluorescence, it's very difficult to decipher the vibrational signature out of it because I will show you in the coming slides that Raman is comparatively weaker process in terms of electronic transition. Okay. This is just to showcase that all the type of spectroscopy which I have written here is related to one or different molecular properties. So I have told you that if there is vibration, then it's related to FTIR or IR. Sorry. And if it is nucleus spin states, we call it NMR. If you have electrons involved in it, we call it XPS or normal X-crystallography. But if you are pointing towards the bonding electrons, we call it electronic vibrations. Okay. So let's just for brushing up history, what history says. Raman spectroscopy was first conceptualized in Russia by this guy Smeagol. So Smeagol actually proposed that there could be some inelastic scattering happening in the system. And what is inelastic scattering? If you compare Compton effect in physics, so Compton effect says that if two bodies are colliding, there is a shift in the wavelength of that particle. So just imagine two billiard balls and the balls are colliding with each other. So they are transferring energy, and that's why there is a change in the wavelength of the system. Similarly, Raman spectroscopy is the optical analog of Compton effect. Okay, so these two guys were involved, and C.V. Raman at that time was in cultivation of science, Kolkata, and his student Krishnan was in ISC Bangalore, physics department. So when Raman moved to Bangalore, then most of the research which these two guys did together is still relevant. We know Raman for doing spectroscopy, but he did a majority of his work in sound waves. How sound waves propagate in different instruments, and how sound waves are actually moving inside the crystal lattice. That was his work after he got the Nobel Prize. So we know that in 1930 he got the Nobel Prize, and immediately he was appointed as the director of Indian Institute of Science by the Queen of England. And by the way, Faraday was the person who, Rutherford was the person who has written the recommendation for Raman. So let's understand schematically what Raman spectroscopy is. Okay. So at that time there was only one source, which is sunlight. So all the major developments, if you see the Newton's famous experiment, Newton also used sunlight. What Raman did is, Raman took sunlight And now you know that sunlight has all the wavelengths. So there he used a filter which only emits violet. So if you see on this side, only violet is coming and rest of the spectra it's blocked. Then he used a liquid. So he used carbon tetrachloride. So carbon tetrachloride, when comes in contact with this violet radiation, scatters light. But if you see clearly, in this scattering, still some violet component is there. That's what we call the Rayleigh scattering. Because in Rayleigh scattering, the frequency is not changing. It's just the elastic part of the scattering. Then he used another filter, which is green filter. Now here comes the brilliance of this man. If you see violet and green, they are complementary in color in the visual spectrum. It means that whatever filter filters violet, this filter will block violet because they are complementary in color. If you plot Newton's wheel, in Newton's wheel the diagonal colors block each other. Okay? So the second filter only passes this green light, and at that time it was his own eye, his own retina that was the detector, because at that time there were no CCTVs, there were no cameras. So there were only photographic plates and his own eyes. So technically what's happening is you are putting an incident light and there are two components. One is elastic scattering, where there is no change in energy at all. And then there is inelastic scattering, where you have two parts. One is known as the Stokes part, and another is known as the anti-Stokes part. Alright? So this is what it looks like. Okay? This is a 488 nanometer laser. 488 means a blue laser. When you put it in cyclohexane, you will see that by naked eye, you cannot see any other color other than the laser's color, right? Everything is bluish. But if you put a filter, the same kind of filter which Raman has used, you will see that all of the blue light has been cut off completely, and you will only see what is coming as a Raman scattering part. So this yellowish tint is different from the laser. So this yellowish color is coming because of the molecular property of cyclohexane. Alright? It has nothing to do with laser at all. So lasers became a very big thing as soon as it got discovered. So we all know that. I don't want to spend too much time. These are the properties of lasers. It's highly monochromatic, means single wavelength. When I say single wavelength, we all should remember that this is not exactly single wavelength. There is a band involved. So when I say that this laser has 633 nanometer, it means that it has 633 plus minus 5 nanometer plus minus 10 nanometer. Depends how sharply you have calibrated. So this laser which I have is a diode laser. But what these lasers are, these are powerful gas lasers, dye lasers, or gas lasers. Like you have argon lasers, you have carbon dioxide lasers. So extremely monochromatic and extremely coherent. Now what does coherent mean? Coherent means, if you see this tube light in this room, all the photons which are coming out of this tube light, they don't have any phase relationship with each other. The phase is randomly oriented. But if I put this laser, all the photons which are coming out of this, they are phase locked. So there is a phase locking interchange between them. That's why I call it coherence. High energy, of course, if you are focusing anything on a very small spot, you will get high energy. There is no doubt about it. And highly directional. That's the best part. If you see this laser pointer, it's highly directional. But this tube light or bulb, there is no directionality. The photons are just flushing around in all the directions possible, right? So there are two kinds of Raman spectrum, rotational and vibrational. We all know that if you are doing in gas phase, you will get rotational spectra. If you are doing in solution phase or solid phase, you will get vibrational spectra. But this is interesting if you see here. The laser wavelength is much sharper in comparison to the Raman wavelength or the Raman scattering. So if I have to put these in perspective, If you get 1 photon of Raman scattering, approximately millions of photons are there which are not shifting from their wavelength at all. That's why the Rayleigh is such a strong background while recording Raman spectra. Alright? So this, we all know that for a molecule to be IR active, there has to be a change in dipole moment, and for something to be Raman active, there has to be a change in the induced dipole moment. I don't want to spend too much time here, but this is interesting. Suppose you have a center of symmetry in a molecule. Okay, there are many molecules which have this, which is known, if you have read group theory, there is something called center of inversion. Okay, so if you have a center of inversion in your molecule somehow, then something very remarkable happens. Then those modes which are Raman active, they will not be IR active. So there is a mutual exclusion between these two. Just to show you the example, this is a spectra of benzene. So the upper spectra is the IR spectra, and lower is Raman spectra. If you see here carefully, wherever there is a peak in IR, there will be no peak in Raman. Okay. Just calculate this peak first. The 992 wave number, it's the symmetric ring breathing of benzene. Okay. So it happens like benzene is breathing. If you see in Raman, there's a very strong signature, and we all use benzene as a standard compound for calibrating our systems. But if you see in IR, there is no such thing. Absolutely zero. And that's the beauty of group theory, that if you have any signature in IR, there will be no signature in Raman at all. Yeah, there are some advantages of Raman, but we all know that. So let's jump to what I have done. So this terahertz spectroscopy is one of its first kind in India. There were reports from Europe, there were reports from US. People were trying it in a very different fashion. What they call it as terahertz time domain spectroscopy, where you actually use time domain. So we all know that any spectroscopy has two parts. Either you do it in time domain or you do it in frequency domain. So if you are recording a UV result, that's a frequency domain information. But if you are doing NMR is a time domain information, right? You change field induction decay and you take that FID signal and then you do the Fourier transform, right? So what I have done is I have actually developed this terahertz Raman spectroscopy, which is just similar to what terahertz time domain spectroscopy gives similar information, but is much cheaper. I'll show you how. So let's introduce what is terahertz. Because this term is going to come in the subsequent slides, so I just want to brush up what is terahertz. This is our normal long electromagnetic spectrum. If I zoom the visible part further, you will see that here is the visible part. This is infrared and this is microwave. Between microwave and infrared, there exists a tiny spectrum which you call sub-millimeter waves. Okay, because they are sub-millimeter in terms of wavelength. This structure of electromagnetic spectrum is where we are operating right now. Okay. So why this range is so important? We have NMR, we have IR, we have everything. So why we are probing this terahertz region? Okay, that's the question. If you see, if you are in the microwave region, you are probing the molecular rotations. It's called a normal rotational spectroscopy. If you are in the mid-infrared, then far infrared region, you are probing the bonding vibrations, right? Stretching, asymmetric stretching, bending. But what happens in this between part is you are actually probing very low energy vibrations. Okay? So crystal phonons vibration, vibrational modes, very feeble interactions you are probing, which are generally not covalent interactions, right? I'm going to show you what all these interactions are. Let's get familiar with this formula. Very interesting formula, very simple looking, but has a remarkable impact on spectroscopy. The frequency of the vibration is directly proportional to the force constant. We all know that. Inversely proportional to the reduced mass of the system. Now be very careful. This is not the absolute mass of the molecule. This is the reduced mass. What do I mean by that? If you have a single gas molecule floating, that mass is the same mass. You take carbon, hydrogen, oxygen, you sum it up, you will get the mass. But if you have a crystal, and suppose there is a crystal exists in a tetragonal state, that tetragonal structure is going to give you a reduced mass. And what is reduced mass? The mass where the center of mass of the system is located. And that's how the center of mass is moving if you are flushing translational motion in it, right? So the beauty of this formula is that if I want this frequency to go down and down, there are only two ways to do that. Simple mathematics. Either you have to reduce the force constant of the system, or you have to increase the reduced mass, because one is directly proportional, other is inversely proportional. Simple. Decreasing the force constant means you are probing low energy vibrations, right? Hydrogen bonding, very weak interaction, van der Waals interactions, and other non-covalent. So all the London forces, dispersive forces, I'm clubbing it into the non-covalent interaction part. Second thing is, if I want to increase the reduced mass, I'm going to take larger and larger molecules. I'm going to take a bulk of it. So something like supramolecular chemistry, you have a bulk of that system, so like a polymer, right? When you take the polymer, what you are doing is you are actually increasing the reduced mass of the system, and hence the frequency will go down. Okay, so these are the only two ways by which you can get terahertz signal, right? Just this slide I show just to tell you that how important terahertz and how important non-covalent interactions are. We all have seen a lizard at our home, right? This is a picture of a lizard sliding over a glass sheet. Okay. Now you see that how beautiful this thing is, that if I zoom on the claws, you will see that there are fibrillar structure. Okay. If I further zoom, you will see that these brushes under the toe of a lizard, they actually don't create suction. We all think that it's moving with suction. Actually, these are the London dispersion forces between the ball and her claws. Okay, and this is the structure which is responsible for the lizard to move out. Okay, it happens so quickly. And just to remind you that these are weak forces. That's why she can put her claw again and again so fast. If the forces are strong, she'll get stuck at one point. Okay, so this is the importance of weak forces in nature. Okay. So as I told you, the origin of terahertz come from different motions. One by one, I want to discuss bending modes, lower energy bending modes. Like you have very high signature. Let's say you have a carbohydrate or a peptide chain, and that chain is just bending. Or you have retinol, or you have vitamin A. Anything which is longer and just bending a little bit. That's terahertz. Torsion and puckering modes. So we all know that cyclohexane chair and board form, right? When the chair flips to board, or the board flips to semi-chair or semi-board, that is very, very small energy change. Okay, that is in terahertz. Intermolecular vibrations, phonon bands. Phonon is very interesting. Phonon is the acoustic analog of photon. So photon is the unit of light, phonon is the unit of sound. Okay. All the phonon bands. So if I tap in this wood right now, what I'm doing is I'm actually incorporating energy, and that energy is transferring through this lattice by phonon modes, which are called standing sound waves. Alright? Another thing is heavy atoms. Suppose I attach iodine with my system, okay, or I attach any heavier system. immediately the reduced mass will go down. And then all the frequency which you are recording then will immediately go down to below 100 wave number. Okay? So anything which involves heavy atom like iodine or any other molecules which are lower in the periodic table having higher mass, they will give terahertz structure. And this is interesting, vibrational modes. We all have seen vibrational modes one way or the other. Basically these are crystal modes. So if you have a crystal, phonon or crystal molecules move in a vibrational fashion. Vibrational means तराजू होता है ना, तो तराजू के दो पलड़े होते हैं. So that means and this vibrational is coming from the sun sign Libra. So Libra has this tarazu, right? This balance. So vibrational means when one molecule goes down, other comes up. So this sort of motion is known as vibrational motion. Okay. So collectively all these fall into the domain of terahertz spectroscopy. First case study which I want to discuss is how drugs enter into DNA. How DNA take drugs. So if you have any problem which is a genetic problem, doctor will assign you a drug and that drug is immediately going to attack your DNA. Now how it happens? We call it drug intercalation. Okay, so drug is going to intercalate in the DNA. So two outstanding questions in this field is that how does DNA open enough? DNA is a compact molecule, we know that. Inside the chromosomes, inside the nucleus, it's a very compact molecule. How does DNA open up? Second is, how do dyes and drugs gain entrance into the DNA? Because DNA will not allow any foreign substance to come inside, right? There is a check in the body every point. You cannot allow any alien element inside the body unless the body accepts it. So these are the two motivations for doing this kind of work. Let's see this. So this is my DNA, okay? And I'm going to put a drug inside the DNA. So inside this is the drug, and now see how the DNA moves. So DNA will get opened up to a very large extent. You see, what you are seeing here are the base pairs. What do you say? A, T, C, G, right? So this is A, T, C, G. Now you see, earlier the DNA was very compact, but as soon as the drug enters into the system, DNA knows where it will go. There is a lock and key hypothesis. We all have read that, right? So DNA exactly knows which base pairs we are attacking right now. So that drug is going to sit between these base pairs, and there will be a pi-pi interactions by which this system is going to be stabilized. These are the two intercalators, very famous intercalator, etherium bromide and porphyrin type structure. Now why we are doing porphyrin type structure? Because if you see the conjugation here, that conjugation on the pi cloud is going to be stabilized by the DNA base pairs. Okay, so what you are doing, you are actually intercalating this porphyrin ring with the basic nucleoside arrangement of the DNA. Okay. So these are the two kind of DNAs which exist in our bodies. Some DNAs are linear DNA, some DNAs are circular DNA. Okay. So if I model this into two parts, I model it as a circular part and as a linear part, what I get is this kind of standing wave pattern. So what I'm doing right now is I'm actually going into a computational modeling and trying to understand how a complex molecule will behave at molecular level. Okay. So this DNA, which looks like a complex molecule, can be associated like a ladder, and that ladder has different springs attached to it, and these springs are of different force constant, because AT, adenine, thymine, that force constant will be different from cytosine guanine, right? So these are different springs of different force constant, and if you model it, we all have done this in our class 11th physics course, where we do that open organ pipe, closed organ pipe, right? You have standing waves and then you calculate where the nodes are coming, where the crust are coming, trough are coming in the sound wave structure. If you do that calculation, you will get a number here, okay? This number is 30 wave number, such a low vibration. You cannot even measure it with traditional IR instrumentation or Raman instrumentation. Such a weak number. If I do take a terahertz spectra, I'm getting a peak at 30 wave number. Okay? This 30 is exactly in correlation with this 30. And that's how powerful this modeling is. I have not done any rocket science here. Just model this complex DNA, know the strength of the bonds, and just translate it into the spring constant structure. Very simple structure, very simple algorithm. But you are getting numbers which are remarkably similar. So this is the terahertz spectra of DNA. Other thing. Let's skip this for a moment. So other thing is that how these motions happen. Like how body knows what to do when an intercalator is coming. Another thing is that what do we need to identify with further terahertz studies. So we were very curious about the structure of DNA and how does DNA takes up these drugs inside it. Alright? So the prime motivation was that many biological processes, not one. I mean, you eat something, any drug, food, anything. All the biological processes are controlled by these kind of low energy motions. And these motions are very stable but very difficult to study. Very difficult. So right now, the state of the art has 4 technologies available. You have filters, you have gas filters. This involves an iodine filter, this is a rubidium filter. Many people have actually tried to incorporate in the microscope structure as well. But the best is, the state of the art is this terahertz time domain, which the West has developed. Okay? Now let's see how it is different. So this is a very interesting thing, and I'll explain as the slide moves. Okay? This is your laser. Okay? This is the path of generation, and this is the path of detection. So there are 2 ways. One, the light is moving through the sample. Other part, you divide the same beam. So this is not a 50-50 beam splitter. This is maybe 90-10, because you need only 10% of the laser just as a reference. Okay? In UV visible spectrometer also there is a reference line. Okay? So now see, you fire up the laser, the beam gets divided into 2 parts. One part is going in the delay. This is terahertz antenna, you get the field induction decay, and this is your sample. Just see how it changes after sample. After sample, this blue part is your signal. Now, at that point, the part which you have divided here and the signal is going to combine. See it again. Beam gets splitted here. Terahertz antenna generates signal. Parabolic mirrors focus the signal onto the sample. Immediately sample gives you a field induction decay. That field induction decay is going to be compared with the original laser intensity. Okay? And that's how you get this spectra. Now I have electric field versus time. I can just Fourier transform it. I'll get it in frequency domain. Simple as this. Okay? What I have done is, I have worked in frequency domain. So no funny Fourier transformation, no costly lasers, nothing. What we did is, we actually took a normal diode laser, let's say a 785 diode laser. We passed this diode laser from a laser line filter to clean it up, and then focused it on the sample. So in this cuvette, it is yellow because I have used sulfur. Okay, so powdered sulfur. Okay. You take the sulfur in this cuvette and then you focus the scattered radiation onto the spectrograph. Now what do you get? So this is how it looks in reality. That's my experimental setup. So This is how it looks if you have no terahertz setup. Okay, this is your intensity, this is your wave number. If you see till 200, there is a high cutoff, and you see the signal, it's saturating the detector. There is no signal at all, everything is buried inside it. But as soon as you implement terahertz, this happens. All the peaks below 200 were buried in the signature. That's how we compare Raman with Rayleigh. So Rayleigh is so strong, just see the counts, 65, 66,000. See the counts here. Although it has been normalized, I can tell you the counts are very, very less. In terms of 60,000, these will be merely 15,000, or if you have the best scatterer, benzene and all, you will get 35,000, that's all. But just compare the Rayleigh scattering with the Raman scattering. And this is what we do in our lab. These are the vibrations which we are probing. Very low frequency, very low energy vibrations. So let's discuss the scheme, how we do that. We took a normal Raman spectrometer, not very costly, not very fancy. We need a single stage spectrometer. People use double stage, triple stage, but no. Just a single stage, cheapest Raman spectrometer, that's it. You take it and you convert it into terahertz Raman spectrometer. So this is the filter which we are using. Very cheap filters. You incorporate these. Oh, by the way, these are called the Bragg filters. Okay. Somewhere here I have seen Bragg's picture. Okay, earlier it used to be. So what Bragg did is, Bragg actually gave you the idea how electromagnetic, especially X-rays, get diffracted from the crystal planes, right? So these are Bragg filters. You put these Bragg filters and you will get this spectra. Beautiful low frequency spectra. You can see the peaks, just see the peaks. 67, 78, 104, 154, 200, 234. These are very, very small vibrations. Very difficult to actually see from conventional IR or conventional Raman spectrometer. So then, definitely when you develop something, you calibrate it because you don't know whether you are seeing something which is correct or not. So calibration is always important, always. I use two systems, sulfur and cysteine. So cysteine is an amino acid, you know that. Cysteine, when dimerizes through sulfur-sulfur bond, that becomes cysteine. Okay. So cysteine means a disulfide cysteine. So this is the low frequency spectra of sulfur. You see the beautiful 43, 50, 62, 83 modes. And if you see cysteine, you will see this beautiful mode at 15 wave number. This is the lowest anyone has recorded in India right now. This is the lowest frequency in India right now. Okay. So 15 wave number, and just look at the Rayleigh. Rayleigh has been reduced to 0. This is remarkable stuff. This is something which cannot be done with the help of normal Raman spectrometer. You cannot reduce Rayleigh to 0, but these Bragg filters are so powerful that they can actually cut off Rayleigh so highly. Then we actually wanted to see, companies have sent us their samples of aspirin and paracetamol. So we wanted to see, now drug industry is panicking right now. Drug industry is panicking because of polymorphism. That one drug, one polymorph is a drug, other polymorph is a poison. So they have asked us that, can you actually see low frequency modes in pharmaceutical, or should I say properly, active pharmaceutical ingredients, AIP, what they call it in pharma industry. This is the spectra of aspirin, acetylsalicylic acid, as they say it. You see the structure, it's like 68, 100, 119, 131, 171. These modes were not accessible through normal Raman spectrometer. And these are the modes because of how aspirin goes in the crystal. So suppose you have aspirin in two different structures. Suppose one aspirin is like pi-pi stacking, other aspirin is having any kind of hydrogen bonding. This can detect. The spectra will change immediately. So it can tell you whether it's a hydrogen bonded spectra or a pi-pi stacking spectrum because the interactions are different. This is paracetamol. It's a very famous drug. And then we actually wanted to see that whether theoretically we are going to get any signatures or not. So we did, and actually there was an agreement, but in low frequency region it's very difficult to pinpoint and say that this is the kind of motion which I want in my molecule. So very tricky. Another example, very textbook friendly, very basic, what we call it as Raman thermometry. We did it just for fun, we never published it. What do we mean by Raman thermometry is that you can actually tell the local temperature of the molecule. Suppose you take a vial of your sample, that vial will be at room temperature, right? But what is the temperature at molecular level? What is the temperature which the molecule is feeling under the laser light? That is what we call Raman thermometry. What happens is, this is benzene Raman spectra, very, very clean spectra. This side, if you see, this is what we call the Stokes side. Okay, Stokes means the energy is going down. So photon is taking energy and molecule is losing energy. This side is known as anti-Stokes spectra. Anti-Stokes means benzene is gaining energy and photon is losing energy, right? If I zoom this spectra, this is what happens. So whatever peak you have on the Stokes side, there will be a peak at the anti-Stokes sides. Exactly same. There will be no exceptions for this. If I take one peak from Stokes side and other peak from anti-Stokes side, I can tell the temperature of benzene. You don't believe me? Okay. Take another example, carbon tetrachloride, very clean structure, very clean spectra. Okay? Just look at this Stokes versus anti-Stokes signature. These are the three Stokes peaks. Exactly at same point, you have anti-Stokes peak. Now take any peak. Let's take this peak and take its counterpart. Just measure the intensity of these peaks or area under the curve, whatever makes you happy. Put this into this formula. What is this formula? Anyone can recognize? What is this formula? Anyone? Boltzmann distribution, right? This is the population in excited state, in ground state, and it's dependent on two things. One, temperatures relation versus the energy gap between these two states. Just modify this formula with respect to the intensity and you will get this formula. Intensity of anti-Stokes versus Stokes directly proportional to the omega-4, and from where this omega-4 is coming? If you calculate Raman scattering by quantum mechanics, you will see that there is a lambda inverse lambda-4 dependence, right? So if lambda is fourth power inversely, it will be directly related in terms of frequency. So omega here is frequency. Just put all these numbers and you will get this T, because Boltzmann constant you know, everything here you know. You just don't know one thing, which is temperature. And that's how you calculate the temperature of tetrachloride or benzene at molecular level. Okay, this is not vial's temperature. This is molecular benzene temperature. Okay, very interesting step. We did this just to make sure that we are seeing our signals at the right position and the system is calibrated enough. Okay. Okay, let's move to some serious stuff now. This is the last part which I want to discuss. This is the thing which we do at last when everything happens. We are famous for two kinds of spectroscopy in India. One is known as femtosecond transient absorption and femtosecond Raman spectroscopy. So now you are incorporating time domain. How it happens? There are two techniques, femtosecond transient and femtosecond Raman. Let me explain one by one. This is your ground state envelope, excited state first state envelope, second state or nth state envelope, let's say. This is the wave function in the ground state. Now when I say ground state wave function, that's a convolution of psi1, psi2, psi3. Psi1 being electronic, psi2 being vibrational, psi3 being rotational. Okay. So when you call rho vibrational or rho vibronic, it means rotational, vibrational, electronic. So this wave function here can be written as a linear combination of electronic, vibrational and rotational simultaneously. But for time being, let's assume that it's purely the ion state. No corruption, no pollution. I excite this. I know the ground state UV visible. I excite it. Now this wave function will be transferred in the excited state, and there's a term called overlap integral. So the ground state function will try to find out its mirror image in the excited state, and that's why it's vibrating. What it's actually doing is it's actually finding its counterparts, its twin brother in the excited state. And as soon as you will get that, you will get a peak in the spectrum. That's what you call ground state UV. Okay. But we are not interested in ground state. We are interested in the excited state UV. What we do when we prepare the wave packet in the excited state, now we probe it. Now whatever lines you are seeing, this will be probed by this wave function, and then you will get the excited state UV. This is not ground state UV. Okay? And this is known as femtosecond transient absorption. Why I am calling it transient? Because the lifetime of this S1 wave function is very less. Decays immediately. Excite, femtosecond, decays. Excite, femtosecond, decays. Alright? Now compare the other part, the Raman part. Similarly, take the ground state wave function, excite it, but now don't probe it with UV. Use a laser, simple laser. What happens? Goes up, comes down. What is this? This is Stokes, right? Anti-Stokes will be going from this and coming back to down. Okay. So this is a Stokes signature of that same molecule in first electronic state, not the ground state. So what I'm telling you right now is that you can do Raman spectroscopy at every possible electronic state. That's the power of femtosecond laser. Okay. That's how it looks in schematics. So I have three beams. One beam, this one is known as the photopump. Photopump means anything which excites it to the electronic state. First, the photopump goes and interacts with the sample and excites the sample. Second, the pair of two beams goes. One is the white light and one is the Raman pump. Same thing which we did. So what we are doing is we are actually calculating ground state absorption, ground state Raman, excited state absorption, excited state Raman in one shot. Okay, you don't have to do 4 different measurements. You can do this technique and you will get 4 spectra in one shot. Okay. Then you block it and the grating disperses the signal on the detector. You read the signal, do Fourier transform, whatever you want. That's how it looks in the laboratory. Okay. This is the laser systems. Okay. So these are femtosecond lasers, phase locked. So the frequency is 75 nanometer, 1 kilohertz. 1 kilohertz is the repetition rate, and the beam is 100 femtosecond. So 100 femtosecond is the width in time domain. Okay. First beam comes. Okay, just track the path. Goes from the delay generator, goes to the grating setup, comes back, again goes to the slit, comes from there, comes there. Here is my sample. Here. Okay. Track the other beam. Other color comes. Now if you see, it changes its color. Earlier it was purple, but after some time it becomes white. This is called white light generation. You have a sapphire crystal and we all know is non-linear properties, right? So when you have one wavelength, you can convert it into white light. You can convert it into 2 omega, 3 omega. These are called NLO properties, non-linear optical properties, right? Track the third beam. Third beam is coming, and it will change its color to blue. So I have 3 beams: white beam, red beam, and blue beam. And these all 3 beams are temporally and spatially focused onto sample. What does it mean? Inside the vial, there will be one focusing point where all the 3 beams will be focused temporally also. Temporally means all of them are coming at the same time. It cannot happen that one beams come and then second comes and then third comes. No use for us. All have to come immediately at one shot, and then you get the spectrum. Okay? So this is a summary, whatever I have showed you so far, that we have actually seen various biophysical, be it DNA, be it intercalators, drugs, various biochemical process to very low frequency structures. We have actually calculated low energy modes for material characterization. I have showed you paracetamol, I have shown you aspirin, we have done that. And then we have actually built indigenous, cheapest Raman spectrometer for terahertz detection, and which can actually go down to 15 wave number. Recent calculations what we have done has gone down to 11 wave number, and that's a record in India right now. So yeah, want to acknowledge few people who are very important for the inception of this lecture. Professor Rai for kindly agreeing for this kind of alumni lecture series. Definitely Professor Mishra for helping out everything. He said that there will be no crowd, there will be no people, but I mean, I'm happy to see some familiar faces right now. Then my research supervisor, Professor Umapati, very kind and very patient man with me. Trust me, I am not someone who can be handled for years and years. He has handled me very carefully. So big shout out to this guy who has actually worked out patiently with me. He's right now the director of ISA Bhopal, but soon be leaving for Mohali. Professor Fred Harris, I mean, remarkable guy. He has actually helped me in understanding physical chemistry, understanding optics, and I owe this guy a lot of things. He has actually showed me step by step how to calibrate the spectrometer. He has worked with me day and night. So this guy, amazing. Professor Chandra Verma, Chandra was in IIT Kanpur before, but then he moved to A-Star Singapore. Very intelligent guy and very exceptionally talented guy in molecular dynamics simulations. So all the DNA calculations which I've showed you, where you can model the base pairs to spring models, this guy told me. And last but not the least, the monetary business. ISC has been kind to give some money for a few years. Then DBT and DST came into existence, so I'm really thankful for these things to get the lab running, get my life running. This is our group. Here am I, and here is my guide. And this is the picture which we have taken a few years back, because now the group has been shrunk to like 2 people, 3 people. So yeah, thank you very much.